what we're starting to do now is we're going to learn how to design. You now know how to come up with member forces in trust, internal member forces, so now we're going to learn how to size the members. Now on Monday, I introduced to some of you, and some of you already know, Young's modulus, the fact that that's equal to stress on strain. And when we have axial stress, that's equal to force on area. And what is strain? Strain is change in length. There's too much echo, isn't there? Okay, is that better? Or you can't hear me at all now? How's that? Is that better? Testing, 1, 2, 3? Okay. Okay, and from these three formula, we came up with a general formula. Just pin this even lower. We came up with a general formula that change in length is equal to PL on AE. If we have a member now that is experiencing an axial force, be it tension or compression, and that member has a length of L, E is its modulus of elasticity, A is the cross-sectional area, then we can work out how much that member stretches or squashes. So that was looking at the deformation, the deflection side of things. Now we're going to look at the design side of things. So knowing all these relationships, knowing that stress is force on area, knowing Young's modulus will dictate how much something deflects and why it's necessary, we're going to look at member design. We went through what a standard stress-strain curve looks like. Is that still echoing? Okay, I'll move it really low. Can you hear me now? Okay. Tell me if it echoes and I'll try moving it further away from my mouth. Okay, we went through what a stress-strain curve looks like, how you have your linear elastic region, which is where you want your structure to be in the day-to-day life of it. How, if you then do overstress your structure, if you are dealing with a ductile material such as steel, you will enter this yield plateau region, you'll get some strain hardening, and then in the end you'll get failure through it necking. What we assume, because when we do design, we are modelling reality. Reality is far more complicated. So we are coming up with simple mathematical design models that are not 100% correct. But they are good enough most of the time. When I say good enough, they're efficient, they're getting our answers right within 90–95%, so we're happy with that. So we assume a simplified bilinear stress-strain curve for mild steel, these two red lines here. And the upper limit is set as our yield stress. So what we're saying is we're not going to rely on any extra strength that we may have through strain hardening, because if we do rely on that extra strength, to actually get there it might have to strain a lot and we might never reach that level of strain. So we don't rely on things like that. So the design criteria for tension loading, members in tension, very simple. When the applied load is greater than the yield point, the yield stress, we have unwanted permanent deformation occurring. So the design criteria is simply that the force acting has to be less than sigma y A, and sigma y is of course equal to our yield stress. So this yield stress value you will generally be given. In the design office, you will look the value up. So you'll be able to find that value. So extremely simple formula. And that's for members in tension. How does something, if I pull it apart in tension, in the end, how much load can I apply on here? The cross-sectional area times the yield stress of the material. So, here's an example. We have a member here, it's 10 mil by 10 mil cross-sectional area. yield stress is 250. How much tension can the section carry? Stress times area. 250 by 10 by 10, 25 kilonewton. So quite a bit of load. 25 kilonewton, 2.5 tonne. So if someone said, I want to hang a car from something that's 10 by 10, will it work? Yes, easy. So, because we're dealing with linear elastic conditions, we can actually always work changes in length out and just add them together. So here we have a case here where we have this tiered structure, could be some multi-storey building. And the question, well, it won't be if it's 40 by 10 centimetres, but get my point. We have some sort of structure here. And the question is to calculate the normal stresses at section AABB under a load of 50 kilonewton. So, if I draw a free body diagram cutting through here, if my load is 50, what is the force in AA? Well, it's 50 kilonewton. If I now have my free body diagram cut through BB here, if my load is 50, the force in BB is also 50 kilonewton. And finally, we work our way to the base. So this structure here is experiencing at each level a force of 50 kilonewton. So very simply, if P is constant for all sections, but the area is varying, all we do is we change the area. So at AA, we have an area of 100 by 50. Our force is 50. We've changed it here to 50,000 because I want to work in newtons. So our answer will end up being in newtons per millimetre squared, which is a compression, which is a megapascals, and it's a compression force. So please remember, Newton per millimetre squared is a megapascal. Our change in length, so the change in length formula we're using here is PR on AE, and the value for L this time we've used is 10 centimetres. So we're working out how much that top area will squash by. So it's simply our load again in newtons, our length in millimetres. If we go back to the beginning, were we told? We weren't told. This was were we told what it is? No, we weren't told. Okay, our cross-sectional area is 5,000, so this must be E, Young's modulus, so it's not steel, it's some other material. So we work out how much section AA shortens, and we do the same for BB. Force on area, we calculate the stress. Of course, our stress this time is a lot lower. In section AA, our stress up here was 10 MPa, and of course our stress will be a lot lower because our area is bigger. We work out the changing length. So this changing length we're working out now is the changing length just in the second part of our structure. We do it for CC as well, and then when we work out the total shortening, all we do is we add them together. It's a linear elastic situation, so we can use superposition. We can work them out separately and then just add them together. So nothing complicated there really, apart from me just saying when you use the formula, make sure your units are correct. Okay, so we are going to do some design now here, very simple. We have a weight being hung from two wires. Now just so you don't forget, because we've been given the dead and the live load here, I'm going to use this as an opportunity to now go back and look at ultimate limit state loading and serviceability limit state loading for you. So, the question asks what size do these red wires here need to be, and how much will this weight deflect down here? So, what size do the wires need to be? This is where we look at an ultimate limit state design. That's a failure or a strength design. And when we do an ultimate limit state design, remember we use the load factors of 1.2 dead load and 1.5 live load. When we come to look at how much the weight deflects, well, that's a serviceability limit state condition. So when we come to do those calculations, we are going to use different loading. We're going to use the same dead and the same live loading, but we're going to use different load factors. So up here for ultimate limit state loading, our dead load is 500. I stay in kilos for the time being. Our live load is 800. So our ultimate limit state load here, I've squashed myself in. I'll just put that one out for now. So that value there is equal to 18 kilonewton. So I'm going to take my load to be 18 kilonewton. However, when I come to look at deflection, the loading I'm going to assume is dead load plus 0.7 times the live load. So that will be my 500 plus the 0.7 times 800, which gives me a load of 10.6 kilonewton. So all strength calculations are going to assume a load of 18, and all deflection calculations will assume a load of 10.6. So we proceed. We want to calculate what size the wires need to be. So of course we need to calculate what the force in the wires are. The easiest, well, there are various ways you can approach this. You can try and solve for the reactions. I'm going to, just as a revision of method of joints, I'm going to say let's do a method of joints about joint C and consider that as our free body diagram. And that blue is a dreadful colour for you to see. So, moving on, let's draw my free body diagram. My load down here is 18 kilonewton. I gave it the numbering system ABC. So this force here, FAC, force to the left, FBC. I'm drawing my unknown forces away from the joint. That indicates I'm currently assuming them to be in tension. So if they do work out to be negative, which they shouldn't here, if you got a negative answer, I think you could safely know that you got something wrong. But if they worked out to be negative, that would be telling you a force is in compression. So I can't say this enough times. What we're doing now is nothing more than equilibrium. I'm saying those three forces are in a state of equilibrium. So I simply use my equilibrium equations. All the forces in the x direction equal 0. Now some of you may be sitting here right now and saying it's symmetrical. So can we just say FCA is equal to FBC? Yes, we can, but I'll prove it for you. Okay? So here, bye. We have FCA. Now that angle in there was 60 degrees. So this is symmetrical. So all these angles in here are 60 degrees. So I have FCA cos 60. It's going to the right. I'm using as my positive sign convention the usual to the right positive, up positive, and anti-clockwise positive. So therefore, when I work out the cos component of FBC, it's negative because it's pointing to the left. And from this equation here, my cos's and 60s cancel out, and I'm left with FCA is equal to FCB. So you probably could have said because my system is symmetrical, the two equal, but I've just proved it for you. Okay, we then go into our second equation. All the forces in the y direction equal 0. So I have FCA sine 60 plus FCB sine 60 minus 18 equals 0. And because these two forces have the same value now, I'll just write 2 FCA sine 60 equals 18. And from this, we end up with a cable force of 10.39 kilonewton. It's positive, so it's in tension. So we know each of our cable forces are 10.39. So let's now do our ultimate limit state design. Our member is in tension, so force on area has to be less than or equal to my yield stress of 250. Here we were told it was 250. MPa. Shush. Oh, yeah.
Shouldn't it be C6 and CD?
Have I got it? Oh, okay. Thank you. So we've got CA and CB. Thank you. As well, above as well. B. Oh, thank you. Come on, someone else have the guts to call out instead of the girl power girl. Okay, thank you. So now we're doing our ultimate limit state design. Force on area has to be less than 250. Our force is 10.39. I'm working in megapascal. What did I say the corresponding units were of megapascal? Newtons and millimetres. So I'm going to straight away convert my force to newtons. And thus the area required here has to be greater than 41.56. What are the units? Oh yes, I'm working in megapascals, units, millimetres, so that is 41.56 millimetres squared. It is a rod section, so this is my pi r squared. So now I'm just making it effectively equal to that. And thus from that, r is equal to 3.63 millimetres. Now this is where you can see some extra factor of safety, because you're not going to go into the shop now and say, I want some rods that have a radius of 3.63 mil, because they're going to say, well, the nearest thing we've got to that is 4 mil or 3.8 mil. So most of the time you'll be putting in something slightly bigger because of availability. So let's say here the radius we can buy is, so I'll write provide. Can I write over that bit there? No? Hang on. So let's say provide our radius is equal to 4 mil. So 8 mil, I don't know if you know, a circle with a line through it means diameter. So let's go buy some 8 mil diameter rods, and this thing won't fall down. Okay, it's strong enough. However, this structure, it's important it doesn't deflect too much. Maybe it's carrying some sensitive machinery, some sensitive measuring device. So we need to also calculate how much it deflects. So let's do a deflection calculation. So now we're doing our serviceability limit state load. Oh, sorry, design. Shh, I can hear you in the back. It's always the people in the very back row, or in the very back. It's not always, actually, but... Okay, when we did our method of joints, based on a load of 18 kilonewtons acting, we worked out our member force, BC, which equals AC, is equal to 10.39 kilonewton. This is for ultimate limit state. But we said now we're doing our serviceability limit state design. Our load is 10.6 kilonewton. So is there any need to do another method of joints here? Or can I just ratio down? I can just ratio down the forces now. So thus, when we come and look at serviceability limit state design, our corresponding forces here will be equal to what they were before, multiplied by the ratio of the actual loading. So when we come and we work out how much this thing deflects, we're going to assume the cable force is 6.11. So the formula... Oh, if you want to. I'm not too particular about my rounding. I always put more than less. Are you on the online quiz? A few people have had issues with number of decimal places. If you're asked to do it to certain decimal places, please do follow the instructions. Okay, how are you going on those quizzes, by the way? Have the majority done it? You have till tomorrow midnight, 11:59. Please do not leave it to the last minute to do it. Okay, but we won't go there now. Come back. Deflection. Shh. If you, after you have done it, are confused and go, oh my God, I can't do this, oh my God, I don't know what I'm doing here, I shouldn't be in here, oh my God, I don't know what I'm doing. Don't panic. Help desk on Monday afternoon and Thursday morning. They will sit down and they'll calm you down and they'll go, that's okay, we'll work through this. You've got the marks to get in here, you can do this, okay? You can. Believe in yourself. I'm being very positive, aren't I? Now, we're working out a deflection now. Shh. But this deflection we're working out is not, yes? Okay, what I've said is, when we way back here at the very beginning said we're doing a serviceability limit state design and ultimate limit state design. So I said when we do our ultimate, we're going to use our load factors of 1.2, 1.5. And when we do our serviceability, we're going to use the reduced load factors. So that means when we design for strength, we're saying the force is 18. When we design for deflection, we're saying it's 10. So we finished our ultimate limit state design. Now we're doing a serviceability limit state design. Yeah, you get it? Okay, good. Now, this formula now to work out how much this time round its tension is going to stretch. Now that amount of stretching is of course not the vertical deformation, it's the amount the cable is stretching. But we'll work out first how much our cable stretches. And I'll just stick to 4 decimal places if that's okay. Always use more rather than less and then round off at the very end. There's my advice to you. The length of these cables, that's 60 degrees in there. That height in there is 4. That height is 4. So the length of this cable here is what? 4 on hypotenuse is sine. Sorry? What's 8? The length here works out to be 4.6188 metres. Yeah? Which is just the sine. Yes? Is everyone with me? Okay. So, we have our length in here. I'm working in millimetres. This is a steel rod. The area now, what we're going to do is we're going to put in the area we require for strength. So we're going to put in our pi 4 squared. And that gives us a deflection of 4.811 millimetres. Now from geometry, as I said, that doesn't tell me, I'm not drawing a very good triangle here, that doesn't tell me the vertical drop. That tells me how much my cable is stretching. So my cable length now is its original length plus the amount it's stretched, 2.811, which gives me an overall length of 4621. Now these support points haven't moved, so that dimension in here, again, just using a bit of trig, is 2.3094 metres. So that dimension in there, 2.3094 metres. So if I now use Pythagoras, so using Pythag now, who we all love, and based on this red triangle, I can say, of course, a squared plus b squared equals c squared. I think you all know what I'm talking about. So if I call that b and I refer to 8, so a squared will be my horizontal length plus b squared is equal to my hypotenuse, and it is my lengthened hypotenuse. That will give me a b value in there of 4003.24 millimetres. What was that length originally? 4 metres. So therefore this thing here has dropped 3.24 millimetres. So you would then go back to the people who are using this sensor or whatever and say, can it cope with that sort of level of deflection? How did I get 2.3? Because this is a 60, 60, 60 triangle, and we worked out that length here, length BC, was 2.4, so that length across there, 4.6 is the same 4.6, so the 2.9 is just half of that. Or you could just say that's rise on run, or that's the cos of 60. So it's just trig again. Okay, moving on, because tension's the easy thing. It's compression. Because I brought my wonderful stick this time, what happens when I squash my stick? It buckles. We call that buckling. So members in tension, nice and easy. They yield. Members in compression, if they're long, they buckle. If they're short, so now I'm just grabbing over this length, if they're short, they'll yield. So things are a bit more complicated. For steel, we can assume the yield stress in tension is the same as it is in compression. And as well as yield failure, we must also consider buckling. When do we get buckling? When you smash your bike. Trying to make this more interesting for you. In the desert when it's really hot due to thermal stresses. Not being able to expand, your pipes will buckle. Here's your railway track again, very, very hot day when all those trains go out of service. Could be because the railway track is buckled, or just here is a finite element analysis of obviously a tower supporting a weight, and the mode case here of failure is buckling. And very famously, what do we know that buckled? Our wonderful... Has anyone been on it? Yeah. It's really lame, isn't it? Well, because I paid the money and went on it with my kids, and I'm like, It's a nice structure, so I shouldn't pick up on the structure. They should pick it up and move it somewhere else. Yeah, it's just this position is not great. But it's a wonderful structure. So you can see here from this article in 2009, the wheel has been closed to the public since last Friday when the operators became aware of buckling in the 38-storey high structure. There was other issues as well, but buckling it was attributed to. So, before we get too much into buckling, we know things buckle about different axes. So my ruler here, I can buckle it one way. If I turn it round and I try and buckle it, it won't buckle about this axis. So a section has two possible axes about which it might buckle. In this case here, let's stick to horizontal and vertical, the x-axis and the y-y axis, and these axes are 90 degrees apart. Now, very important you understand what is the buckle axis. People say, Lizzie, what is the buckle axis? When you consider the buckle axis, you consider it relative to the cross-sectional area, not the length, okay? You consider the cross-sectional area here. And the buckle axis divides, when I buckles like so, the top of my member, is it stretching or squashing? Stretching. So the top half of this member is in tension, and the bottom side of this member is squashing. So the bottom side of this member is in compression. So the buckle axis divides the region in tension, the region stretching from the region squashing. So in my section, if I call this XX and YY axis, which axis does my ruler buckle about? the XX axis. Whenever I push it, okay, it buckles about this axis, because this axis is dividing the top, which is in tension, from the bottom, which is in compression. I can't get it to buckle about its YY axis. It's too stiff. Well, if I applied enough and stopped it buckling the other way, I could get it to buckle. If I put this between a brick wall, if I stopped it buckling that way, by putting this between a brick wall and I push down on it, in the end it would buckle the other way. So the buckle axis divides the region of the beam in compression from the region in tension. So here you can see, sorry, because my mic's so low, I'm banging into things. So you can see here, if I buckle it that way, that region there is the, you can't see it very well, the compression region. Whereas in this picture here, I've tried to draw it for you, that region in there is the compression region. So my axis separates what's in compression from what's in tension. We deal primarily with one-dimensional buckling. When you get to second year, my students now are they're coming to terms with different axes of buckling, biaxial bending. Okay, here is my formula. We're not deriving that formula for you. We're giving you the formula. It's called the Euler buckling formula, named after Leonhard Paul Euler, who was a preeminent mathematician of the 18th century. And if you ever do a quiz, who was one of the best, greatest mathematicians of all time? Euler. He made heaps of important discoveries in calculus, graph theory, mechanics. He decided, let's call the symbol pi, pi. He decided I was good for imaginary units, so he was a cool mathematical dude. So looking at our formula, P is the buckling load. This little e here stands for Euler. So our buckling load is a function of pi squared, EI on L squared. This E here, I'll talk about it in a few minutes, in about 10-15 minutes. This E here doesn't stand for Euler, it stands for effective length. So we'll go there soon. E is Young's modulus. If I have a very stiff material, it's going to be able to carry more load before it buckles. So buckle load is directly proportional to material stiffness. The stiffer material will carry more load. The length of the material here, my beam gets longer, my load gets smaller. What's she talking about? If I all write y is equal to 1 on x squared and I ask you all what that looks like, you're all going to go, what are you all going to do for me? That. Yeah. So when x gets bigger, you know y gets smaller. When your length here gets bigger, your buckle load gets smaller. I can buckle this easily. When I start shortening the length, I have to apply more and more load to the system. Now the final term in this equation is the moment of area, or second moment of area, or the moment of inertia. We're going to spend a whole lecture on that later. For now, I'll give you the value. You'll be given the value of that for the problem set next week. Just a stretch. Okay? I is the geometric stiffness of the section. Which axis is my ruler weak about? It buckles easily about that axis. Okay? So the stiffness about that axis is very weak. If I turn it round, it's far stiffer. So it's a geometric feature. So just for now, if you just remember, for a rectangular section, I is equal to BD cubed on 12. That's something you will remember. Okay? It's very common. If we're dealing with a circular section, I is equal to pi out of the fourth on 4. If it is a hollow section, I is equal to the outer minus the inner I. So if I have a rectangular hollow section here, the I here will be the BD cubed on 12, I'll call it of the outer dimensions, minus the BD cubed on 12 of the inner dimensions. And that's the same if you want the cross-sectional area. You go BD outer minus BD inner. Now in terms of this B and D, I'll say a little bit more. What is B and what is D? I'll have an overhead, but I'll just tell you now. If we say this is our axis of buckling, because you all know what an axis of buckling is now, you always take, if the formula is usually given, well, you memorise it as BD cubed on 12. So in this formula, B is the dimension that we say is parallel to the axis. So here, if I'm buckling about the XX axis, it would be BD cubed on 12. If I was buckling about the YY axis, it would be DB cubed on 12. Okay. So just have one more overhead on what this second moment of area or moment of inertia is. It's a geometric property. My ruler here has a length of 950 millimetres. It is 37 millimetres wide and about 5 millimetres thick. If I say where's the cross-sectional area, you can all see this. This thing has a geometric property called the stiffness, and we said that geometric property, if for a rectangle, is BD cubed on 12. And then you're going to say, but what does it mean? What does it actually mean? Think of it as measuring how far the section is spread from its centroid or its neutral axis. So my ruler here, I'm drawing the cross-sectional area of the ruler on my head here. The cross-sectional area is here, so that's about 37 millimetres, and that's about 5 millimetres. Now, it buckles about this XX axis. When it buckles about the XX axis, can you see that material is effectively sitting on that axis? However, if I now turn my ruler sideways like so, and I try and buckle it about this axis, I'll call this time the YY axis, can you see that area is spread further away from the axis? So that makes it stiffer. So what's the most common steel section you can buy? A universal beam. Have a look at our universal beam shape. Here's my neutral axis here, and I've got a big blob of steel far away at the top and a big blob of steel as far away at the bottom. So a universal beam is a very stiff section. Okay? So think of it, there's my axis, it's far away. So looking at this, which axis is stiffer about? This axis, because it's spread further from the axis of bending. Okay, as I said, we've got a whole lecture on that. When you come and do your project, you have got a similar table for your square hollow section. In your project, you're designing with square hollow sections, but looking at this table, and I actually will refer to this table now, the first column is the section size. So here it's a 350 UB92. In your tables, it's a 250 by 250 square hollow section by 3. So this dimension here represents the width, the depth of the beam. Now in this table, you can see a cross-sectional area column here. That tells you what the cross-section is for your section. So when you come and do your project design, once you've got your geometry sorted, your loading, you've done your method of joints, your method of sections, and you have a force, you're going to come into here and say, okay, here is my areas. Now, it doesn't say on here, but in your table, I think you're told it's C300 steel. It's either 300 or 350. When you see 300, that means your yield stress is 300. So look at your tables for your project and see what that number is, and that will tell you what the yield stress is. So you then, all you need to do for your members in tension is get the load, force on area is equal to yield stress, the area required has to be greater than my load divided by my yield stress. So you're going to grab your old, divide it by the yield stress, get an area, come down this column here, this one here, sorry, and find an area in here greater than what you need. Is that clear? It's as simple as that for members in tension. You get your load, you divide it by the yield stress, that's the required minimum area, and you'll find an area here, and then go, okay, that's what I need, so that's my section. So the project design part is easy. Now, for this particular universal beam here, it has two different axes of buckling. So you'll see a moment of inertia Ix and Iy. In your square hollow sections, because it's symmetrical about two axes, you'll only see one I value. Oh, speak of the devil. Here it is for your square hollow sections. So here is your area column. So you'll need that. And here. Your steel is grade C350. And if you read the small print down here, it tells you that means your yield stress is 350 MPa. So from your area column, you'll be able to choose an area and say, okay, the section I need here is a 50 by 50 by 1.6 square hollow section. So if you use that section, that dimension is the 50, that dimension is the 50, and the third number here is your thickness. So tension design, easy peasy. Let's go back to buckling. If you get confused about this buckle of axis, what's she talking about? A section always buckles about its weaker axis, the one with the smaller I value. So you can always work them both out and say it's going to buckle about the weaker one. For a circular hollow section, square hollow sections, the axes are the same. You don't need to worry about it. So going back to it, a member in compression has two possible failure modes. It's either going to buckle or it's going to yield. We don't know which it's going to do. Let's look at this buckle curve in a bit more detail here. As I said here, if we just look at the relationship between buckle load and effective length, it looks like your y is equal to 1x squared, 1 on x squared curve. But what this formula is telling us is that when our length gets really, really small, our buckle load goes to infinity. And that's not possible. That's what people forget about yield, and they say, oh yes, this member here can carry 2 million kilonewton. It can't. The greatest load it can carry we call the squash load. The greatest load it can carry is equal to the yield stress times the area. So we in effect have a failure envelope. So rather than work out which type of failure we have, what the standard procedure is to do is check both cases. So if I assume it's going to yield, this is how big it has to be. If I assume it's going to buckle, this is how big it has to be. And then I choose the bigger of the two. So long members fail by buckling, short members by yield. Where is that crossover point? We don't bother trying to find it out. We just check both things. So in tension, you just check yield. In compression, you check yield and buckling. Do we need a break? Okay. Have a break. Have a Kit Kat. Any questions, come and ask me now. Here somewhere. That one?
Yeah, when you're finding the delta L, you said with the units you're using there, the pi 4, where's that from? The pi 4?
We said over here, this is in the radius of 4 mil.
Yeah.
So we've taken that area.
Oh, the area.
So that's the area required for strength.
Okay, yeah.
And so we're going to say, okay, we're going to work.
Is that just sort of like a ratio?
We could do a method of joints again. But we're doing the same thing.
What's the basic load?
It's killing you as well. I have a question about these. How do you assume that it's symmetrical? Just by that answer?
I should have actually it looks symmetrical. Yeah.
But
Because
in a,
it's showing it's symmetrical. If this was in an exam, I probably would have 60.
okay, cool. Good. Because I thought that's an assumption.
No, I'm telling you it's symmetrical.
Okay, thank you.
Okay. Let's move on. So where are we? We are here. Okay. Once again, this is a formula. Once you know how to use it, there's no issue about using it. But where people commonly make errors are with the units. So once again, you need to be consistent with your units. I'm not saying use the correct units because you can use whatever combination of units you want as long as they are consistent. But what I highly recommend you do is use newtons, millimetres and megapascal, because a megapascal is a newton per millimetre squared, and normally when you're given the value of E, you're given it in terms of megapascal. And this I value, well, this is a BD cubed on 12 term, and these dimensions are usually of the order of millimetres. 100 by 200, 50 by whatever. So I, what are the units of I? Millimetres to the power of 4. So usually length in your diagrams is given to you in metres. Just remember to convert that to millimetres. And when you do so, your buckle load will come out in newtons. So you can work in whatever units you want. That's just the one I would recommend if you ask me which units to use. So down here your length is metres, or millimetres, sorry, and because it's squared, you get a millimetre squared term down here, so you can see it all cancels out and you're left with newtons. Oh, there you go. Okay, so just very quickly, let's just do some calculations here. We have a 10 millimetre radius solid steel rod. We know the yield stress. We're told the yield stress. We've given the Young's modulus. We're just going to calculate the buckle load here for various different lengths. So we're going to, we really should say, draw the buckle curve. So here, it's a 10 millimetre rod. I don't need the area. My notes, I've got something else here, but I won't go there. Oh no, I do need it, because we're drawing the buckle curve. I shouldn't actually, I'm going to rub that out too. And I'm going to say, draw the failure envelope. So drawing the failure envelope there, we need to know what our yield stress is and our cross-sectional area, which is pi r squared. So plugging into that, I get an area of 214 millimetres squared. Moment of inertia, I said for a circular section, pi r to the 4th on 4. Gives me that value. We're given E. So in terms of my buckle formula. Pi squared. I'm going to work in megapascals and millimetres to the fourth. Length is my variable here. So when I do plot this here, so at 1 metre length, I'll graph it. I'll do some values. When L is, I'll start in millimetres, 300 millimetres. My buckle load here is 172 kilonewton. When L here is 400 millimetres, my buckle load works out to be 97 kilonewtons. So the answer I will get out would be in newtons, and I'm dividing by 1,000. When L is a metre, I get a load of 15. At 2 metres, can you see, because it's L squared, how quickly my load drops? When my length gets to 4 metres, my buckle load is as little as, my member can carry as little as 1 kilonewton. But when it's 300 mil long, at that length there, I'm saying I can carry 172 kilonewton. But I haven't got 4 metres here, but assume this was 4 metres long, it would only be able to carry 0.97. So if I draw that, it actually is a very steep curve in there. But the question is, can my member actually carry 172 kilonewton? Let's calculate our squash load. Our squash load is as it's called. What's the load that will cause it to squash, to yield in compression? So my squash load here is my yield stress times my area, which was 250 MPa times the area I worked out earlier, and that actually gives me a load of 78.55 kilonewtons. So basically I can't reach that 172. I have a cut-off limit here, and that cut-off corresponds to the squash load limit of 78.55 kilonewtons. So my failure envelope is a combination of both curves, so it sits in like so. All good? So we are going to go back to the problem we did half an hour ago. And this time round, we've put our structure upside down, so we don't have to calculate our forces again. All our forces will be the same. But this time, my cables, are they in tension or compression? Compression this time. So, do we have to calculate the squash load, or have we done that already? The squash load is the yield load. So, I will just go over a couple of things. So, from the previous problem, for ultimate limit state design, we said the force in our members was equal to 10.39 kilonewton. Now, based on yield, be in the failure criteria. So based on stress, which is force on area, has to be less than our yield stress here. Our area, we got an R value. We've done this calculation already. We chose an R value of 4 millimetres. Because that yield check we did in tension is the same as it is in your compression. So based on this thing not buckling but yielding, we need to have a 4 millimetre diameter rod in there. Is that okay with everyone? Radius. So this is the radius. Yep. Okay, so now let's do our buckling check. So buckling, pi squared EI on L squared. What's my buckle load equal to? I'm going to set my buckle load to the compression force in the member. So I'm going to set my buckle load to be my 10.39 kilonewton. So I'm going to now equate that to pi squared times my Young's modulus. And this time round, I is my unknown. What is my length from the previous problem? We worked out the length here, just using trig. It was 4618, close enough. So can you see in your formula now, we're saying how big does it have to be? Okay, it has to be able to carry 10.39 kilonewton. So let's define that to be our buckle load, and now let's work out how big the member has to be. So based on that, I don't have an I value, but this is a circular section. So the I value here for a circular section is equal to pi out of the fourth on 4. So I substitute that value in there, and when I do so, I get, so this term on the right here, this is my acting force. This has to be less than, no, I've got it the other way round, greater than. So when I work out my R here, it has to be greater than or equal to this number here, which you can get when you plug into your formula, and that will be millimetres to the fourth. And easiest way to go from R to the fourth to R, square root on your calculator, instead of to the power of a quarter. Just square root it twice. So here we get our radius now, to stop it buckling, has to be greater than 19.44 mil. So let's now say, okay, let's provide a 20 mil radius, 40 mil diameter rod. So what is the critical failure mode here? Yield or buckling? Buckling. So here, buckling is critical. What does that mean? If I put a section of 39 diameter in there, it will buckle. It won't yield, but it'll buckle. So which one will it do first? Buckling. So now we know the section now, 4 mil isn't big enough. Now we need 40 mil. So we can go through that whole deflection thing again. So going through that whole deflection calculation again, the axial deflection now, PL on AE, when you plug the area now of 20 mil in, so our load as before was the 6. This time now when we put an area in there. Is there a horrible smell in here? What have you done? People in the back row. Did someone, I can't imagine that is a F word, because someone can't let out that much gas to fill the whole lecture theatre. That's off. I thought something was burning. What did you release? Something toxic that we're going to all die with? I'll open the doors. They're hot air risers. Who did it? Did someone do it, or is something gone? Oh, I'm not going to ask. I'm not going to get an answer anyway, am I? Okay, so we're going to work out the deflection here. So this time round, is our cable going to stretch as much as it did before? No, our area is far greater. So our cable, well, it's not stretching now, it's actually shortening by a very small number. And I'll leave you to use Pythagoras when you actually work out the vertical drop here. You get a very small value. So a very negligible small value here. So you can work that one out yourself. I think I'll show you something. To inspire you. Okay, this will inspire you to be a good engineer. Our Westgate Bridge, it's not the most exciting bridge in the world. It was built in 1968 to 1978, took 10 years to build it. Design engineers, Freeman Fox and Partners. It is what we call a steel box girder cable stayed bridge. You can see the cable stays here. Oops. So it's a combination of a cable and a beam in terms of the structural forms bridge. The main span is 336 metres. As I said, it is not a very exciting bridge. The reason I'm showing it to you is it actually collapsed during its construction. I don't know if you're aware of it. And how many people died? 35 workers were killed when it collapsed. And that was unfortunate because their workers' huts were under the bridge. So most of the workers weren't on it when it collapsed, they were under it. And that's why it took 10 years to build it. The erection method was what we call balanced cantilever. So as I said, the erection method can sometimes be just as well, it's just as important as the final structure. During the erection phase, it acted as a cantilever. So the balanced cantilever erection method, you build out from either side of your supports, you get to the middle and you pray like hell, they're both at the same height, and then you connect them together. And what happened was they built out and they weren't at the same height. So 2 years into the construction in 1970, not the main span, a 112 metre span, side span collapsed. As I said, 35 workers were killed and 2,000 tonne of steel plummeted into the mud banks of the Yarra. And apparently you could hear the noise of this from kilometres away. They were using this balanced cantilever method of construction, and on the day of collapse, at the point of joining the two sides, there was a vertical discrepancy of 114 mil. So we're talking big, steel, heavy, 2,000 tonnes. We're going to join it together. We've got a gap of 114 mil. So what do? They say, engineer, come out and tell us what to do. Now, nowadays, you would be using laser levelling as you went out, and you would be compensating for it, okay? But in 1970, this structure, this cable stayed structure, this plate girder structure, was new technology. It was new in the 70s. Here you have the fallen bridge here. So here is the trapezoidal bridge cross-section after failure. So it's a steel girder bridge, very thin steel work. Okay, so very thin plate here. You can see the cars hanging down here. So what do you do if you have 114 mil discrepancy? Have you heard of the word Kentledge? Kentledge is basically dead weight. What you do is, what they did was they put 10 concrete blocks. They said, bring out the blocks, 8 tonne each. So they loaded one side to lower it. That's what you do. That's what they did. There's a discrepancy. It's harder to lift up. You're up in the air. You load the other side a little bit more. And that's the way they constructed, and it was all very well and good. It was because it was this new plate girder design. So each one of these tonnes deflected it downwards. But there was all this extra weight on the actual structure, and they hadn't connected it all out. So they started connecting it up, but with this extra weight on, they found that bits of this plate here started buckling. Okay? So each of these sides of this bridge here, there were 2 sides, and there's a plate in here and some nuts that joined it all up, and they found that these bits of plates were starting to buckle. So when something starts to buckle, you say, well, let's undo. So they started undoing the bolts. So the longitudinal joining was half complete when the orders came through to remove the buckle, which they tried doing by removing the bolts. So as the bolts were removed, the whole thing fell down. Now, this was not like the Hyatt Regency, where we can come up with the cause of this. In a couple of minutes, I can explain it to you, and you can clearly see the cause. It was actually, the failure mode was very, very complicated. And they had a Royal Commission. So the report from the Royal Commission into the failure took months and months and months. And the 70s was the time when Monash actually was founded, and some of the leading professors here, Professor Noel Murray and Paul Grundy, who are since deceased, were actually in that Royal Commission. And what they did was they brought to Monash parts of the Westgate Bridge. So at Monash, unbeknownst to you, we have one of Melbourne's best sculptures, outside Building 60. So next time you're outside Building 60, go and have lunch next to that scraggy-looking sculpture there. And that scraggy-looking structure is parts of the Westgate Bridge that were brought here and tested. And I think it's an amazing structure because it looks like the steel has just ripped apart like paper. So you can see here the buckle. So here, you'll see it started to buckle, and this plate in here is buckling. So how do we remove this buckle? Let's undo the bolts. And because it wasn't joined together, there was too much weight on it. It was still acting as a cantilever. You can see here the steel. I mean, this just looks like it's been ripped like a piece of paper. And you can appreciate the forces that came into play here to do that. So please do go and appreciate this sculpture, because it's a wonderful sculpture. And it's amazing to look at and to think this is very thick steel. Anyway, going back to it, the Royal Commission. The reasons for the collapse, they concluded in the end, are found to be in the acts and omissions of those entrusted with building a bridge of a new and highly sophisticated design. You build to the design codes, something goes wrong, you follow the codes, you won't get sued. It's not your fault. What they were building here, plate girder structures, there was no design code in place to cover this. This was new design. So The Westgate Bridge was not the only bridge that fell down. Similar bridges at the time in Britain and Europe were temporarily closed and checked for safety. In England, it was a similar, well, there was also a failure for similar buckling reasons, and I think in Canada there was also another failure. So design and construction methods were fully reconsidered by the Westgate Bridge Authority before work began again in 1972. So in 1970-71 there occurred the failure of steel box girder bridges at Milford Haven in the United Kingdom, the Westgate Melbourne in October 1970, and Koblenz, Germany in November 1971. So should we stop showing initiative? No, but sometimes failure occurs, so we have to be very, very careful in all new design. So lessons learned from the failures, yes, the Royal Commission into the failure of the Milford Haven carried the title Inquiry into the Basis of Design. It led to the production of new rules for the design of these structures, and those rules were then used to design the Westgate Bridge. So the conclusion, they concluded effectively there was not a single cause of failure. It was not just the removing of the bolts, but it was the failure of the design engineers to consider the structural design, including the erection process. So both the design engineers and contractors were blamed. The design engineers because it was said they failed to give proper and careful regard to the structural design and to check the safety of the erection proposals put forth by the contractor. So once again, I suppose the same issue with the Hyatt Regency. The contractor changed things. This time round, the contractor didn't change things. They tried to come up with a procedure, but the design engineers didn't carefully look at it. They probably looked at it to the best of their ability, but they didn't appreciate the problems. And also it was due to the erection method proposed by the contractor required more than the usual care. So they did as well as they could, but this was new design. So please go and have lunch on that sculpture. 1 minute break. Are you ready to launch back in? So do you have to know how to design for buckling? Yes. Most definitely. We may as well get on with it. Okay, does this problem look familiar to you? Yes. We analysed this using method of joints, method of sections. Now we're going to design it. So when we analysed it, not in yellow, in red, we got 15 compression. I'll just write all the forces down in here. And this is what you are going to do for your project, so pay attention. You are going to do your method of joints, and writing a little bit neater than me, you are going to draw a lovely diagram of your structure, of half your structure if it's symmetrical, and rather than tabulate the results, you may go, remember AB in a table equals that. Because your structure is not that big, I would say actually draw your structure in stick form and actually record on it the forces. If you want to write the tension forces in green and the compression forces in red, or highlight what's compression and what's tension with a green and a red highlighter, it's up to you. Whatever clearly shows what the forces are. So we have done a method of joints, we've done a method of section checks, and here are our member forces. Okay, we are now going to design some members. We're going to design the worst, the tension member with the highest tension force in it, and a compression member with the highest compression force in it, just for this exercise. So, our greatest tension force is our 21.2 kilonewtons. So, we are designing these as square hollow sections, and from our table we can see We're grade C350, which means our yield stress is 350 MPa. So, its intention, the only failure mode is yield. So our force on area has to be less than 350 MPa. So our force here is 21.2, has to be less than 350 MPa. The subscripted required area has to be greater than 60.57 millimetres squared. So we come over to our section table and we're going to look down this column here for an area just slightly bigger if possible, bigger than 60.57. So we come down here, our areas are really big. Oh, in actual fact, our smallest section is big enough. So you would say the smallest available section is sufficient. So therefore, provide that section was a 20 by 20 by 1.6 square hollow section. And when you do your reports to save us going and checking, the area of which, tell us what the area is. The area is 111. So I can see straight away, okay, our section has an area of 111, we need 60, it's all good. So there is the design of your member's intention. So that will do you for AC. It's a small structure, put it in for CE. You can check, you would have to check all your compression members as well. Now, let's now just look at our biggest compression force. And as well as that being our biggest compression force of 15, that's also appearing in the longest member there. So it's just not biggest compression force, it's the longest member as well. So now let's do our compression design. So our maximum compression force is equal to, what was it, 15 kilonewtons, and the corresponding length of that member is 2 metres. So now checking buckling. We would set our buckle load to be 15. So P, the force acting has to be less than our buckling capacity. So in here, E for steel is 200,000. We said our length was 2 metres, so that's squared. So rearranging this formula, I'll now call it I required. Has to be greater than 30,396 millimetres to the power of 4. And don't do what I just did in your project presentations. Don't say, and the I value has to be greater than 4.6 by 10 to the 12, and for that it has to be greater than 222 millimetres, because no one's listening to me, are you? It's all going over. So the I value has to be greater than what I've shown there. So don't talk lots of numbers. Everyone switches off. So let's go back to our table. We're looking for an I value greater than 30,000. When you look at the I values here, so it's this column here. And you can't see it very clearly, but in that column there, that there says 10 to the 6 millimetres to the power of 4. So therefore, if I go back to my, I value and change this to units of 10 to the 6, it has a value of 0.0 0.03 by 10 to the 6 millimetres to the power of 4. And you know what? Oh, yeah, okay. So coming down that column there, the smallest I value is 0.006, and we're looking for a value just greater than 0.03. So can you see it there, 0.0316? So we want an I value which is greater than or equal to 0.03 by 10 to the 6. So coming up our table here, this column here, I, it is that value there, which makes it this section here. So that is required. So now I'll just say from the tables, I haven't checked yield yet, from the tables, a 30 by 30 by 1.6 square hollow section has an I value equal to, hang on, which one? I can't read that. I've got to look at it up there. No, it's 2.5, isn't it? Sorry. 2.5 has an I value equal to 0.0316 by 10 to the 6. Can you see that? So that value, that section would do nicely. However, quite often in these problems and in the exam, you're asked to come up with minimum weight sections. So when I say that, if you come across here to the cross-sectional area, you can see it has an area of 259. Now, if we move up that column there, if I consider this section here, a 35 by 35 by 1.6, can you see it has a smaller area? So, in a smaller area means a smaller weight. So can you see here, because my section is bigger, because my area is spread further from the neutral axis, it's actually a stiffer section. So if you have no stipulation, the section has to be as small as possible. The architect doesn't say to you, no, it's got to be a 30 by 30, it can't be a 35 by 35. You would then go for the minimum weight section. So from the tables of 30 by 30 by 5, has an I and a weight here of, let me get this right, 2.03 kilograms per metre. However, if we now look further at the tables, we will see that a 35 by 35 by 1.6 square hollow section has an I value equal to 0.0379, but weighs less. It weighs 1.63 kilograms per metre. So what's the most efficient section? It would be your 35 by 35. Now at this point here, you would then say, okay, force on area. You would get your force on, you would put in your force of 15 kilonewtons. You would divide it by the cross-sectional area, and you would get a stress value. And if that is less than 350 MPa, you would say, therefore, your section is okay. So that's your yield check. So this now is our yield check. And that is based on the area from your cross-section. Okay, so we've now checked it for buckling and yield. So be aware, people tend to, when they move up the table there, look for the first value they hit and say that's the answer there. But the more efficient section would be the 35 by 35. Okay, one last thing I need to talk about. So I'm not going to work through this problem because you can work through it yourself. Is what that little e on the length means. Because I said to you that little e on the length does not stand for Euler buckling. It stands for effective length. So while I am talking quickly, I'm going to pass this round. You probably all won't get to it. I'll bring it next week as well, or in the classes next week you've got them. What I want you to do is squash it with your fingers like so, and then I want to grab it with fists like it's rigid, and then squash it. And feel the force, and you'll see that you have to apply a lot more load when you squash it like that compared to squashing it like that. So we'll start there, and you can move up. And don't hit anyone in the head with it. So come this way. And the reason for that has got to do with the effective length. So in this formula here, LE refers to the effective length. For trusses, for your project design, the effective length is the truss length. When your ends are pinned, your section buckles like so, your length is actually equal to your effective length. So as part of the project, length is effective length. But generally speaking, the definition of the effective length is the distance between zero moment points, or points of contraflexion, or points of inflection. In layman terms, well, not layman, because laymen don't know what a sine curve is, but you all know what a sine curve is. I want you to think of it as the distance over which you get a half sine curve when it buckles. What do I mean by that? There is a column there with two pen ends. And if I draw the shape of that buckle curve, can you see your half sine curve in here? Is L. So your effective length is L. However, I'll do this case here. You're now grabbing it top and bottom, and watch the way it buckles. The way it now moves is, remember, at a fixed support, there's no rotation at the fixed supports. So can you see when you think of your half sine curve, the effective length for your half sine curve is now half the length. And the other extreme case is when you have what I call a flagpole. When you have something that's tied in at the bottom and free on the top, think of that middle case as you have a parachutist that is about to land on top of a flagpole. So he lands on the flagpole and the whole thing will just bow sideways. So where's your half sine curve? It's actually double the true length. So your effective length is now 2 times the true length. So how much more are you squashing it by when you grab the ends, when you fix the ends, compared when you pin them? You have to apply 4 times the load. How do I know that? We'll do the calculation quickly. But just showing you quickly, note, I'll show you quickly here, pi squared EI on length effective squared. Now when this effective length is just equal to L, as compared when that effective length is equal to 2L, or if it's equal to a half L, can you see, because it's squared, you're squaring the 2 term, so it's a quarter the strength. When you square that half term, it has 4 times the strength. Why is this significant? Because in multi-storey buildings, whether you choose to pin the end or fix the end will actually determine how much load your members can carry. So let's look at 2 real-life conditions, even though they're only shown as sticks on there. You're building a carport. Your carport has to be accessible from all 4 sides, so you can't put cross bracing in. Cross bracing is the easiest way to stabilise a structure. When you go out driving and you see those hay sheds and they're all leaning a bit, well, they haven't got any bracing in their foundations, they're all leaning over. To create a stable structure, you need to ensure no side sway, and the easiest way to achieve that is to put cross bracing in your structure, and it's usually hidden in the walls of the structure, or the actual cladding you put on provides that stability. Where you can't put that bracing in, what you have to do is you effectively have to create that flagpole condition. So in this situation here, I've got a flagpole. Over here, I say I have a pin-pin column situation. because this wants to move sideways, and can you see the cable here? It's triangulated. We'll stop it moving sideways. So if you load both those structures up to failure, how will they buckle? You can see there the two different buckle modes. You have the pin-pin case here, and here you have the fixed free case there. So your effective length here is 2 times your true length. Your effective length here is equal to your length. So, oops. So based on that, if you plug into your formula, you'll see the buckling capacity of these columns here is 1/4 what it is in the cross-bracing case. So if you have to provide lateral stability by a fixed base, your columns have to be bigger. Now, as well as your columns have to be bigger, I've shown the concrete support here is the same size. They will also be different, because to stop this column moving, you will have to put a much bigger concrete pad in there. Then in this region here, if you get some rotation, if your foundations do rotate a bit, it doesn't matter because your base is pinned. So this solution is the more expensive solution. So if you're building something more than a carport, a glass structure, and the architects say, no, I can't show any cross-bracing, of course it can be done. You'll do it by fixing the bases, but you'll say to them, okay, we need bigger foundations in there, and our columns will have to be bigger. How about you just make a feature of the cross-bracing, expose it, and make it look nice? That's the choice. Is that clear with everyone? So what your columns are doing affects your whole structure. So final problem. Let's actually do some numbers rather than me just talk about it. We have 3 10-metre long columns. They all have the same size. An I value of 80 by 10 to the 6 and a Young's modulus of 200, so they're still. They have 3 different end conditions as shown. What is the effect on the buckling capacity of these sections? So this significantly affects the buckling capacity. So let's look first at our pinned ends. So my effective length is equal to my length. So for this case here, we were given Young's modulus, we were given I. You assume this is a rectangular section, so it has the same I about both axes. And in here now, working in millimetres, I'll stick my 10,000 in, and I get a buckle capacity of 1,579 kilonewton. Now, I'm not doing the yield check as part of this. I'm just comparing my buckle capacity. Now I'm going to look at what I call the fixed free ends. With a fixed free end, the only thing that changes now is the fact that my buckle load now is 20 metres. So it's 20,000 squared. So in this case here, my effective length is 2L. Up here, my effective length is L. So I said that reduce the buckle load by 4. And that is equal to 1579 by 4. So it has 1/4 the strength. So the buckle, the end conditions can be very significant as to what size your members are. Now the final case is fixed ends. And in this case here, our effective length is half. I'll just write it as EI this time. But when I come and plug in my effective length, it's now 5 metres. That's squared. So my buckle capacity is 4 times. So that's equal to 4 times my simply supported pin-pin condition. So look at the difference in strength. So it's 14, the fixed has 14 the strength of the fixed free. Now when you come and do your project, if you are designing a single span bridge, you are not going to assume it's supported by the surrounding buildings. You're going to have columns there. Because those columns are so close to the building, we can actually tie them horizontally into the building and assume the top of the column isn't free to move. Okay? So if you just have those columns to design, assume it's pin-pinned. However, if you have the case where you have decided to have a 2-span, this is the building, this is the building. So what I'm saying is when you put a column in here, we can tie it into the building and assume this buckle length here is equal to L. Now at this point here, the top of that column, is there anything holding it horizontally in place? No. So for this column here, you would have to build in a proper foundation in here. That's not part of your design. But you would design this as fixed and free. And you could say, some people go, oh, but the bridge is supporting the column. No, the bridge is loading the column. The bridge, can you see, it can still move a little bit sideways. And if you have that little bit of movement, you have to conservatively and assume it's free. So in this case here, you would say your effective length here is equal to twice your length. So be aware of that. Okay. How about I let you do this question at home? Okay. Just one last slide here. In all the problems we've been doing and in your project, your section has had 2 axes of symmetry. So your IXX is equal to your IYY. Last bit, just give me 1 more minute. 1 more minute. Standard sections, though, universal beams have 2 axes. So in an instant like this, if you were, this has an effective length of 3 metres, it carries a load, find the most efficient universal beam that will not fail by buckling. Which I value would you choose, the bigger or the smaller of the 2? So our formula, so we know this value, this value is 500. In here, should we put the bigger or the smaller? You have a think about that, and I'll talk to you briefly about it at the beginning of the next class. Okay, any questions, come and ask me. Otherwise, have a good week.